Okay, here we go with the chain rule. It's a set of slides I saw from another textbook, one that I've used before, not for a while though. But I thought you ought to see this because it gives a different look to some of the things, and it might help you understand it just a little bit better. So here we've got a function. You can tell that it is a composite function because the large function, and you get the ink here, the outside function is a cubing function. The inside function is x squared plus 4. So we've got a composite here, a function inside a function. Remember, you can rewrite this as long as you let u be the inside function, x squared plus 4, then we can rewrite m of x as u cubed. It makes things a little bit simpler. Now, if I want to take the derivative of m of x, remember I treat the outside function as regular power rule, and I keep this x squared plus 4 intact. Don't touch it. So I bring the 3 out front. I don't touch the x squared plus 4. Since this is the general power rule, this 3 gets reduced by 1, so it's squared. And we haven't done anything with the x squared plus 4 yet. We still need to take the derivative of the x squared plus 4. Well, let's see what it is. If I took the derivative of that, it would be 2x. So that's times 2x. There's my derivative of that composite function. We can slide these two together. So 6x times x squared plus 4 quantity squared. And there's our derivative. So function m is a composite of two functions. An inside function, this is the inside function, and this is the outside function. One note that we usually don't have to concern ourselves with in business calculus is the fact that the domain of m of x, in other words, what numbers can this x take on? Well, the domain of that is a set of all numbers that come out of g of x. So g of x is the domain of f. Don't worry too much about that though. So we've got another one here. F of u is e of u, and g of x equals minus 3x. Find f of g of x and g of f of x. So this takes us back to pre-calculus or college algebra. So let's start with this one first. We want f of g of x. So we start with the outside function. What does the outside function look like? What we're going to do is we're going to take the outside function, and where we see the x or whatever variable that is, we're going to just leave it blank. Well, the outside function is f of u, and it's e to the u. But instead of putting a u in there, we'll leave a blank. Because u represents another function. In this case, g of x. Now, what is g of x, the inside function? Minus 3x. So we'll put a minus 3x there. And that is our first result. And that is f of g of x, composite function. Incidentally, you can ignore this if you like, but if you've seen this notation before, this for composition of functions, it means we take this x, g gets it first, and the result is seen by f. It's the same thing as we've got here, just a different notation, just in case that's the way you've seen it. Okay, that's part 1 here. Part 2, we're going to take g of f of x. So all we've done is we switched the roles for g and f functions. So let's see what this looks like. So we're going to look at the g function, but where we see the variable, we're going to leave a blank, just like we did with f. So g is this. So g looks like this, minus 3 times some missing number. Now what goes in there? This goes in there. So put e to the u, that's f of x. And what do we get? We get minus 3e to the u power. Alright. Not the same. Take particular notice of that. They are not the same. So you cannot take f of g of x and just swap them like this. They're not the same ordinarily. In very, very special cases, they might be the same, but typically they're not the same. Let me get rid of those marks for you. Erase a link on the slide. So there's where we are right now. G of x is minus 3 of x. And there's our first composite function, our second composite function. Next, write this function as a composite of two simpler functions. This would be the inside function because if we were evaluating this, we would have to do that first and then send it to the outside function. So we could say, if we want to call f of x the outside function, it would be 100 e to the u. And what would g of x be? G of x would be the inside function, which would be 0.04x, which we call u. These are our two functions. There's the outside function, and this one's the inside. Two simpler functions. Okay. The inside function is what would be done first if someone actually gave us the x. We'd have to finish this before we took the square root. So the square root being the second thing we would do, is the outside function. And g of x will be the inside function for minus x squared. And over in the previous one, I referred to this as the square root of u. And this is our second one. So those are the two simpler functions, square root and 4 minus x squared. Now remember the power rule? Of course you do. You can do that in your sleep, can't you? Bring the n out front, reduce this by 1, and there's the result in general. So what if we could use the power rule to take the derivative of a composite function? That would be pretty handy. So it's a specific case. It doesn't work all the time, but it works some of the times for the chain rule. So it's nice to remember. So u of x is a differentiable function. So y equals f of x, and f of x is this. So we bring that n out front. There's your n. And you reduce that power by 1. There you go. And at the end, you have to take the derivative of the inside function. So, highlighting that, the derivative of f of x, there's my n out front. U of x, notice I haven't changed what's inside, but I have reduced the exponent by 1, and then I'll take the derivative of the inside function. And there's the chain rule as a power rule, a general power rule. It works for anything that has a power like that. Two other ways you can write it. This might be handy for you. That's a really nice, short, concise definition of the general power rule. Or you could write it like this. If you like the notation that Leibniz had, this is a good one. So how about this one? This is the outside function, and this is the inside function. Take a look back here again, if you like. So, the outside function, if we want the derivative of x, bring that 4 out front, leave the 3x plus 1 intact, reduce this exponent by 1, and then take the derivative of what's inside. The derivative of this part would be a 3. And there's our derivative. A little bit of cleanup work at the end here, because we can multiply the 3 times the 4 and get 12 times 3x plus 1 cubed. There you go. Excuse me. Let's clear those inks. There we go. Bring the 4 out front, reduce the 4 by 1, take the derivative of the inside function. A little bit of work there. We found the derivative, and we've changed the 4 minus 1 to a 3. And there's our final answer. How about another one? You want to pause it and see if you can do this one? See you in a second. Okay, you're back. All right, we're going to take this a little bit faster. Y prime equals. Bring that 7 out front. Leave this alone. Reduce the exponent by 1, so it's 6. And then we'll take the derivative of the inside function, 3x squared in this case. And then I'll slide this out front, and our derivative would look like this, 21x squared, and then x cubed plus 4 to the 6th power. There you go. And they got the right answer too. Isn't that nice? Next one. Find the derivative of this. Remember, all this says is, it's the same thing as saying y equals this part right here, and then finding y prime. That's all it means. So if we do that, first of all, we might want to rewrite this thing. D dt, that means we're going to take the derivative with respect to t, because t is our variable. Now, I'm going to rewrite this because it's not ready for the power rule yet. So t squared plus t plus 4 to the, got it? Minus 3 power. Now I'm ready to roll. So first of all, bring that out front. I'll have minus 3. I have t squared plus t plus 4. Subtract 1 from that, I have negative 4. Did you put it negative 2? I hope not. And then take the derivative of what's inside. The derivative of what's inside would be 2t plus 1. You didn't forget the 1, did you? Finishing up, we have negative 3 times 2t plus 1 times t squared plus t plus 4 to the negative 4. And if we want to clean it up a little bit more, I'm not sure we need to, we have negative 3 times 2t plus 1. Are you ahead of me? We have t squared plus t plus 4 to the 4th power. How's that? Let's see if they got it right. Rewrite. Use the power rule. Take the derivative of what's inside. Rearrange it a little bit, and you can see they got exactly the same thing. So give them a hand on that one. They got it right. Next, Theorem 2, the chain rule. So first of all, these derivatives have to exist. If this is a composite function, then this is the outside function, this is the inside function. So we take the outside function, leave this part alone, and then take the derivative of the inside function. Now if you're wondering why they happen to use E and I, E would be the outside function or the external function. And I guess you figured out this will be the internal function. Inside, outside, external, internal. Whatever you like, whatever really sticks with your head. Another way of doing the same thing is to say, okay, u is going to represent a function, like up here. Instead of writing I of x, we'll just write u, and u is going to be a function. And then we'll write aside u equals I of x. A little bit more compact when you look at this part, but it does take 2 sentences to do it. So, what does that mean? Well, we can say this a different way. This m prime of x, we can just call dy dx. That's what we want to get in the long term. On the right side of the equation, we take the derivative of y with respect to u. In other words, we take this part right here and take the derivative, but since there's a u in here, we take it with respect to u. And then on the second one, we'll take the derivative of u, remember this is u, the inside function, with respect to x. Notice that if you look at this, you're looking for dy dx. That's what you want. If you look at what's on the right-hand side, notice that there's a du and a du. If you cancel those out, if you could, and you can, what would you get? You'd have dy dx. This is just another way of getting dy dx, assuming that both of these actually exist. So let's try it with this one. Let's see what happens. Remember, we've got an external function and an internal function, or an outside and an inside. And this is how they're going to do it. So first of all, your external function is this one, and the external one is that. So E of u equals u. Remember, we're going to just let u represent the internal function. So first of all, we're going to take the derivative of this. Then we'll take the derivative of this, and we'll have everything that's ready to go. So here's the derivative of that one. That's pretty easy. Bring the 3/2 out front. Reduce the 3/2 by 1. You get a 1/2. Over here, this one's pretty easy by itself too. Take the derivative of this. We've got the internal function's derivative. And bring that 2 out front. We've got 6x. So by the chain rule, we can write it like this. Now this is dE, external function, du. It's this part right here. And then we multiply times du dx. Remember, this is u, and this is u prime. So we put those together, bring that 6x out front, you get 9x, and you still have this part. And there's your derivative. An alternate way of doing it. You might think that's even better than the other way. Let's see. Let's take a look at another one. See the inside function and the outside function? So what is E of u? Remember, this is the inside function. This is the outside function, E of u. Nice and simple. And what's u? The internal one has x's in it, alias u, and that's 2x cubed plus 5. So, since we know we're going to differentiate, why don't we go ahead and do it? This would be dy du, and remember, I mentioned the other day how easy this one is. Just e to the u. Done. On this one, what's du dx? It's 6x squared. So what's dy dx? It's dy du times du dx. Fill in the blanks. Dy dx equals, here's dy du, which is e to the u, and du dx is 6x squared. But remember, u is this, so our final answer would be dy dx equals, and bring that 6x squared out front, and replace the u by the 2x cubed plus 5. And there's our derivative. I think this is what Leibniz would have liked, but until we can ask him, we'll have to let that pass. So here's our inside function, and then let me get rid of that for you. There's a slide gone. So here's our outside function, our inside derivative, and there's our final answer. Same as we got. Next, another one to look at. So what's the external one? The external one, let's do it this way. So m of x. M of x is the natural logarithm of some function. Make it simple. Just replace this by u, where u is what? The inside function, x squared, minus 4x plus 2. There's our inside function. Now we know we're going to differentiate these, so this is u. dm du equals, and the derivative of this is pretty easy, 1 over u. Over here, what's du dx? Well, this is pretty easy, 2x minus 4. Now we'll put them together. What we want is dm dx. So we take dm du, multiply that by du dx. What do we have? dm du is 1 over u. du dx is 2x minus 4. We have to replace this u that was there temporarily. U is this value up here, so we'll have 1 over x squared minus 4x plus 2, and we've got this 2x minus 4, that's on top. So, putting that all together, we've got dm dx equals, now look down here, we've got 2x minus 4 on the top, and we'll have x squared minus 4x plus 2 on the bottom. And there's my derivative. Using the chain rule a little bit different way. Let me get rid of this inking for you. Erase the ink. There's using I of x for the internal one. We call that u. So we've got the external one is natural log of u. The external one. So we've got this, we've got the two derivatives, so by the chain rule, we can write it like this. This is dm du, and this is du dx. Put it together, and there's our derivative for this function. So this is the one that I mentioned the other day. This is the one your book shows you. Remember, one way of looking at this is if you want to find the derivative with respect to x of f of g, g is the inside function, f the outside function, take the derivative of f and leave g alone and multiply it times the derivative of g. Okay. Can you find the derivatives of these two? So let's see about this one. Here's the inside function. So I'm going to call y e to 2x. I'm going to let u equals the inside function. And I'm going to take the derivative after I rewrite this one using u instead. E to the u and here's my u. We'll take the derivative of this one very easily, e to the u. We'll take the derivative of this one, u prime, or du dx, dy du, in case you want to keep track of that, equals, and that's just a 2. So I want dy dx. I can get it by taking dy du, that's over here, and multiplying it by du dx, which sort of lets these two cancel out, and I get the correct answer, but in small pieces. So dy du is e to the u, that's this part right here, and du dx is 2, so dy dx equals 2e to the, and the u is 2x, so there's my derivative. On the second one, let y be natural logarithm of x squared plus 9. I'm going to make things easy by calling u the inside function like this. That makes y the natural logarithm of u. Nice and simple. Then we'll take the derivative of both. So y prime, or let's use this notation, dy d. Now remember, we've got a variable of u here, so it'll be dy du equals, and this is just a nice 1 over u over here. Du, d what? Well, there's the x. So u x. What's the derivative? Well, that's easy, right? So we've got these already set up for us. Now what I want is dy dx, and I can get that by multiplying dy du times du dx. Remember, these sort of cancel, so we still have the dy dx. Now I'll fill in dy dx equals dy du is right here, 1 over u, and du dx is right here, 2x, or 2x over u, but this is what u is, so my final derivative for that one is dy dx equals 2x over u, which is x squared plus 9, and I've got my derivative. How cool is that? So you have two different ways of taking the chain rule and using it on a composite function. Let me clear that up for you. Erase all ink. So there we go on the first one. Taking the derivative. Second one. And we get the derivative for that one. One more step. And we've got it. And last of all, let's see if we can do this one. So, let y equals, now the inside function is this, so I'm going to say let u be the inside function, sort of get that out of our hair, so to speak. So the y is just u cubed. It's easier to work with those. So then, dy, d what? du equals, that's easy, 3u squared. What's du, d what? Well, there's the x. Equals what? Well, the derivative of this is 0, so that helps. The derivative of this, oh, this gets a little bit more interesting, doesn't it? We need the derivative of this, which means we need to use the chain rule on that one. Well, let's see if we can get through this. E to the x squared. Well, let's stick with this. We're not going to get rid of everything here. Since we've got a composite function that has another inside one, let v equals the x squared, because we've got a function inside a function inside a function. Oh, that doesn't sound good, does it? But let's take the pieces. So what do we have here? Du, d what? Well, we make this u into 1 plus e to the v, making everything a little bit easier, because v is x squared, so we can rewrite the u that way. Make everything as easy as possible. So we've got du, d what? V now. Equals. So what's the derivative? Oh, that's easy. There's 0, just e to the v. We're not making this hard, we're actually making it easier, even though it's more complicated. And we'll take this one. We need to take the derivative of that. dv, d what? Well, there it is. dx. And we just get the 2x there. We're in business. Now, watch as this comes together. What we want is dy dx. What do we have? We have dy du, and we have du dv, du dv. Notice these du's are going to sort of cancel out like. And we've also got dv dx. Do you see what that's going to give us? The du's cancel, dv's cancel. We actually do get the dy dx. Now we just fill in. dy dx equals. What's the dy du? Right here. 3u squared. Du dv is e to the v times, and dv dx is 2x. So that's what we've got so far. Now let's back substitute. So we're going to move up here, and we're going to get that dy dx that we need. First of all, the 2x is fine. Leave that. We've got a v here. We shouldn't have the v in dy dx. What's v? Well, right here, v is x squared. So this part right here is e to the x squared. Well, what's 3u squared? What's u? Well, 3u is up here. U is this. So we've got 3 times 1 plus e to the x squared. And that's our u. Now we can put them together. So we finally got dy dx. And we can rearrange these terms a little bit. We can bring the 2x out front. 6x. Bring the e to the x squared here. And the 1 plus e to the x squared there. And we've got our answer. This is the derivative of this doubly complex or composite function. All right, I hope you're able to follow that. You might want to watch it again because it is a chain of a chain. So it gets a little bit interesting, but notice that by just working through it, making it simpler and simpler and simpler, taking the derivatives of each one of these, and then filling it in to get dy dx. Those cancel, you actually do have dy dx after you substitute in. Where you've got the u's, you're going to replace them. Where you've got the v, you're going to replace it, and the 2x is fine. Let's see. Let's clear this up for a second here. Maybe you'd like to see that work better. So there's our first one, and the next one, and the next one, and there's our final answer. All right. We'll see you later. Bye-bye.